Living in a technological civilization, it is rather hard to think of a bigger brain as a disadvantage, but as we'll see today, that is often the case. So today, we will be wrapping up our look at the great filters of the Fermi paradox, those conditions that are thought to act as major hurdles to technological civilizations arising in the universe. Previously, we've looked at those conditions for the planet that might make intelligence uncommon, but today we want to look more at the evolutionary steps to get to human-level intelligence, and also the hurdles you need to pass once you have that to get to true technology. Now, for all purposes today, when I say intelligence, I am principally referring to human level. We often use the terms sentience or sapience to further subdivide levels of intelligence, but the definition of sentience is terribly vague and can be interpreted to include pretty much anything with sensory apparatus and a basic brain, whereas sapience is not really in the common lexicon and essentially means wisdom. Since wisdom is a trait often lacking in some humans, and also a trait not necessarily required for technology, I am disinclined to use that either. So we'll be sticking with human-level intelligence, and I think context will make it fairly obvious when I mean any intelligence at all or human level. As always with the Fermi paradox, since it is a question of why we can't see or hear any aliens, it is also important to remember that at the moment, that only means aliens with modern technology or better. Our brains are more or less identical to the folks who first figured out agriculture and metalworking, but we could not detect such a civilization ourselves right now. So if it turned out going beyond that point was very uncommon, you've got your answer to the Fermi paradox right there. And it might be uncommon. We'll spend the last section of the episode discussing that, and challenging our general assumption that once you have tool and fire use and sufficient brains, you inevitably transition to high technology. But before that, let's consider some key steps of evolution needed to get to more or less modern man. There are quite a few of them, and even those which have happened more than once so that we cannot view them as a fluke, often took a lot of time, which is another key point of the Fermi paradox. The universe is young, and the period in which life could plausibly have existed is shorter than that. The odds of a given solar system having life should generally tend to increase with time too, except where changing conditions could make a planet uninhabitable, such as the sun it is around growing hotter over time and sterilizing it. A key aspect of the great filters approach of the Fermi paradox is that it is not about if a planet might eventually support a technological civilization, it's about whether or not they already do, and currently do, for a given value of current since light and signals take a long time to travel. So as an example, over a long enough period of time, any given planet that had basically identical initial conditions as Earth ought to produce life. But we do not know what those conditions are, or what the mechanism is, in any rigorous sense. If we assume it is underwater thermal vents, a planet with less of them should take longer on average to produce that first abiogenesis event. And yet, we do not have a good fix on when life began on Earth. The most optimistic model is 4.28 billion years ago, while the oldest undisputed life is at 3.5 billion years. That is between 130 million years and a full billion years for life to arise after we had oceans. And for my part, I have to raise an eyebrow at some people who refer to that time duration as almost instantaneous. We are also making a big assumption to think that is an average. That is justified by the mediocrity principle, which tells us that when we only have one example of something, or even just a few, we should assume that example is fairly normal. But that's just a generalized approach to take in ignorance. If you land on an isolated island, and the first person who greets you is wearing a hat and carrying a pair of binoculars, it is a good idea to assume that is normal here until you meet other folks. Except that the binoculars probably are the reason that person was the first one to greet you. Nonetheless, the mediocrity principle is usually a good first approach. Not, however, when you are dealing with a circumstance that has the word paradox in it. We label stuff that way when the available evidence makes the situation seem impossible or freakishly improbable. At that point, you want to challenge any circumstances where you haven't got a lot of data and are making assumptions. We already know abiogenesis is horribly improbable, because the requisite chemicals and conditions existed in the trillions, interacting constantly, and still took a long time to go from that to alive. A man who wins the lottery on his 10th ticket with no other data thinks that that is normal enough and will, by the mediocrity principle, assume most folks win after about that many. And if winning the lottery comes with having to go someplace to pick up the prize, most folks he meets there will be big outliers themselves too. It's only when you actually know the number of winning and non-winning tickets that you truly understand the odds. Before that, it's just guessing. So the question is really just, is this abiogenesis event so freakishly improbable it takes countless quintillions of atoms 100 million years to produce a basic life form, or just a bit more freakishly improbable so that it would normally take the sample 1 trillion years to cough up a life form, but we lucked out early? Up until the moment we can model the probabilities for a given solution producing a basic life form, we cannot say. And there are probably many thousands of valid most basic life form configurations and a wide spectrum of specific environments they can emerge from. We haven't got a clue if abiogenesis happens on short timelines in virtually any plausible chemical soup, or was a 1 in a million event to have occurred here that fast, and should be a great filter all on its own. I will categorize it as a possible great filter, but we will otherwise bypass it today. One other thing to keep in mind though, is that while we have a window for life to have emerged that's about 800 million years wide, from 3.5 to 4.28 billion years ago, if life did arise on the early end of that, it means the next big steps took a lot longer, making them much better filters. Unicellular life, initially in the form of bacteria and archaea and later joined by eukaryotes, ruled alone over the Earth for billions of years before multicellular life came about 900 million years ago. But even that immense time span does not do justice to the sheer generational scales involved. Some bacteria can multiply once every 20 minutes in ideal conditions, but let's be conservative. Say they would have multiplied once only every 5 days. That is still 2 trillion generations to the dawn of multicellular life, which is comfortably more than the 1.5 trillion stars in our local group of galaxies. That doesn't even count the number of actual organisms, only the number of generations. Mammals multiply considerably slower, in the order of months at the quickest and a decade or more at the slowest, and we have only had 320 million years since our early synapsid ancestors to multiply. Looking at generations alone, mammals are effectively nothing more than a blink of an eye when compared to the unicellular realm. We are dwarfed into obscurity when we further compare the sheer population sizes involved. So even though multicellular organisms appear to have evolved separately on many occasions, leading us to reasonably believe that this is not a particularly improbable event, it's worth remembering that it still was less probable in terms of raw generations and population than every other mutation mammals have experienced combined. Some mutations did result in revolutions, even amongst the unicellular organisms, like the development of photosynthesis in cyanobacteria 2.1 to 2.7 billion years ago that ultimately changed our atmosphere to become oxygen-rich. This provided a vaster energy source serving as the bottom of the food chain, and a much bigger total population. And that speeds up mutation by allowing more events. Another big one was being able to share mutations through viruses and plasmids, allowing for the sharing and swapping of genetic material. When organisms can't swap DNA, then you can have billions of mutations going on, but only in series. Another big step forward was sexual reproduction about 1.2 billion years ago. That sped things up too. In a way, we can think of that as when evolution really kicked into high gear. 2 critters of fairly similar DNA classified as the same species, rather than every organism simply self-dividing and diverging from those around it. And that took about 2 to 3 billion years. Had it taken even just 4 billion, our own sun, which is constantly getting warmer, might have rendered the Earth increasingly barren and eventually uninhabitable before we arrived. So this entire sequence of events could be seen as a pretty strong filter too. Yet it doesn't particularly interest us today either. Our focus is more on intelligence. That can be a fairly arbitrary term, and to make things worse, we also have good reason to believe muscles, neurons, and even brains, for a given value of brain, have evolved separately more than once too. It's not something limited to vertebrae. Indeed, since many plants demonstrably react to their environments, the only reason we can say plants won't evolve brains is because they simply provide too much cost for too little benefit to them. That, though, is a big thing to remember. Most tiny animals have way more generations than we do, connecting them back to our common ancestor, and in that sense, they can be seen as more evolved. They reproduce faster and in larger numbers, both in terms of litter size and often total population. Your cat is more evolved than you are. Indeed, chickens, rats, and rascally rabbits even more than they. Yet they're not that smart, and very generally, the faster and more numerous a species reproduces, the dumber it is. You nod now. Brains are big energy investments, take a long time to grow, and that is true and important, but at the moment think of it in the sense of catching up. Some species evolved a cool new trait that makes it breed slower and in fewer numbers, and all its rival species have a lot of room to narrow that gap. It's been around 1,000 human generations since our mutual ancestors started keeping cats and dogs around, but for them, it's been more like 10,000 generations. Add to that, we have been bootstrapping at least dog evolution during that time, and often breeding for intelligence. Chimpanzees, at least, one of our closest relatives and competitors for intelligence, do take a long time to reproduce, pretty parallel to humans, and again that comes from the long development time for brains. And most of the other critters that are demonstrably smarter than cats or dogs have generations much longer than a year or two. That is one of the first markers about intelligence. It is an expensive investment, not just to run a big brain, but to grow one in the first place. It takes a long time while the young critter in question is highly vulnerable and realistically cannot fend for itself. We cannot rule out that some alien might be human-level intelligence, yet use the strategy of laying thousands of eggs and leaving them to fend for themselves, but it does seem quite unlikely. More important than that is recognizing that higher intelligence is not, as we usually think of it, automatically beneficial. Quite to the contrary, even ignoring the upkeep cost in growing and maintaining a big brain, it has some big disadvantages. I can toss you a ball and you can catch it, so can your dog. Whether you realize it or not, it took an insane amount of brain power to pull that off. What we think of as a conscious mind is a tiny little iceberg tip poking out from a massive supercomputer below the surface, and in many ways it's less of a peak than several, acting like a committee. A basic reactionary brain is very helpful. It reacts fast and gets stuff done. Your conscious mind is more like a committee discussing everything. Picture someone feeling thirsty and grabbing a sip of water, versus some huge committee meeting to discuss water safety standards and a year later releasing a 300-page report. That big brain is wonderful for developing complex and abstract strategies, and thus science and technology and poetry. But it's not great for dealing with a lion jumping out of the bushes to eat you. Simple, fast action is typically the best, and a big brain that likes to stop and ponder stuff can get you killed, and in fact it did get us killed a lot back in the day. We did not evolve as an apex predator, and if you told just about anyone from pre-modern times that we should be worried about lions or wolves going extinct, that notion would be so bizarre to them, they'd probably assume you meant to say we should be worried about it not happening fast enough. Now, it would be silly to say, on a planet dominated by human technology, that bigger brains don't help with survival, but there is a threshold, and probably a fairly narrow maze to navigate in evolving a brain capable of complex abstraction and problem solving without it becoming a survival hindrance. Tons of critters have big brains. Most of them have had them for more generations than we've had our human or near-human level one. So either the next couple key steps require a lot of improbable flukes, or most of the time, any improvement isn't an actual improvement from a survival perspective. We still know so little about intelligence, human or animal, that it is impossible to call this transition zone an improbable one, but it is my own best guess for the biggest filter on going from animal to human intelligence. Relatively large brains have been around a long time, and in species that have had many generations, so simply getting a bigger brain itself is no problem. It's getting one that doesn't become a survival threat. And when you consider the sheer amount of resources we have to pour into a kid, or that chimps or dolphins or elephants do, compared to even a rat, let alone an insect, we can see how that happens. High intelligence and conscious thought are often going to represent a fatal disadvantage to a creature in a species, not an advantage, and breeding slowly with huge inputs of resources didn't advantage humans much until we had it for a long while. There are so many occasions in the last couple million years where we barely clung on, rather than dominating the ecosystem as now. Keep in mind most of the folks in our genus aren't around anymore, and there's no consensus that we did any of them in, let alone every species of them. There's a sci-fi novel by biologist Peter Watts called Blindsight that explores this in more detail. He makes some very strong arguments about how valuable intelligence and consciousness really are in there, and I strongly recommend it. I don't want to spoil it, since it is also our SFIA August Book of the Month, sponsored by Audible, and is essentially a mystery, so it's hard to discuss without spoilers. But if you didn't find my arguments about higher intelligence to be universally good or particularly compelling, I'm sure his will do the job. It definitely shakes up the conventional view of intelligence, and offers an interesting solution to the Fermi paradox. Regardless, species have survival strategies, and the big brain route requires committing to a few: small litters, long upbringing time, long lives, and heavy interdependence. Lone wolf species are not well suited to benefit from giant brains, too likely to die before reaching maturity without protection, too hard to benefit from specialization when you need to be a jack of all trades. But just because you've broken that barrier into a reasonably human-level brain doesn't mean the job is complete. Once you've made that leap, something only we have really done, doesn't mean the job is done. In the 2 or 3 million years we have been around, our crawl to technology has been abysmally slow till maybe the last 10 or 20,000 years. We got fire, very handy, but it took us a long time to apply that to making ceramics or metals. In all the time before then, we had used it to stay warm, to keep predators away, to fire sharpened sticks, and to cook meat. So imagine a species that had sharp claws, thick fur, was an apex predator, and could digest raw meat better than we can. Fire doesn't help that much, and the stuff is terribly dangerous. They will probably never invent metals or ceramics because even if they do invent fire, it is a dangerous device of little value to them. We evolved during a series of ice ages when the planet was generally cooler than normal, and we ourselves came from a warm part of it and don't particularly have warm fur, even when we were hairier. Odds are pretty good that most species that get to the big brain zone don't really need that, and that is the main reason you hang around by a fire for protracted periods and might ponder it and its other uses. We think fire was invented possibly as far back as 2 million years ago, but 600,000 years is the loose consensus for definite regular use. Definitive use for cooking only goes back 200,000 years, but it's hard to say if that might not go back a lot further. Cooking food helped us digest it. We actually have an awful digestive tract for an omnivore, and we should assume that is abnormal. Digesting food you have already ingested and not maximizing what you can get out of it is a bit of a weird oversight. Possibly a very fortunate one for us though, since it not only meant we need fire to help with that, but it might have been a big factor in agriculture. More on that in a moment. But our crappy digestive system might have been very fortunate. So we already need a few unrelated mutations: longer lives, longer maturation, bigger brains, and a preference for tribes or clans, to be able to truly take advantage of high intelligence. And again, the big point of evidence for it otherwise being disadvantageous is how many other critters have had decently large brains as long or longer than us. More generations evolved to catch up in the brain race, and still have not done so. It's probably not that hard a mutation, just typically not handy. The octopus is an intelligent creature in that it is good at problem solving and can learn and apply that knowledge. Recent genetic evidence says their intelligence evolved around 400 million years ago. Why then are they not the dominant species, having had such a long evolutionary head start on us? Perhaps it comes down to them lacking those traits I mentioned. They are solitary, live in an ocean where fire is not an option, and have short lives. Now we have the issue that most of our early technology just isn't that handy, particularly if you don't have hands. A lion doesn't really need anything sharper than its claws for survival, but would still benefit from being able to hit a deer at range with a sharp stick or get leverage by swinging an axe. But holding or swinging something is quite hard without the right anatomy, and actually aiming to hit something at range with a stone or spear is much harder. It took us a very long time to make and improve such things, and if they weren't as beneficial to us, even if they were somewhat beneficial, it probably would have taken longer and maybe never. Someone might invent a paperclip in the absence of paper, but it's not exactly a device that will awe the tribe and get passed on to future generations. Our tribes were not that big, they couldn't be, and couldn't afford specializations or knowledge retention that didn't help the tribe in an obvious way. We have found that a lot of critters do prefer cooked food over raw food. Apes will usually pick a baked potato over a raw one, for instance, when offered, so we don't want to assume you have to gain a huge benefit from cooked food to do it. It also helps you store food. Still, storing food is a pretty abstract concept. Most critters do not do it, and the ones who do are not engaging in a learned behavior that involves conscious thought, so it's not like a squirrel is going to think about cooking food to store it like he does nuts, and for that matter such critters usually store food that lasts longer without being cooked. The other thing about fire, of course, is that it keeps predators away. Not all predators and alien predators might be different. What's more, alien planets are often not going to be well set up for fire. I don't mean because they lack a decently dense oxygen atmosphere either. We covered that in the rare Earth hypothesis conditions last time. You need an environment where stuff can get dry, and a lot of plants might be way more humid or rain more often too, or have much faster plant decay. Decent odds are one of our ancestors was sitting on a nice soft bed of dried grass to be comfortable while relentlessly banging some rocks together to sharpen them, and got fire that way. Odds are also good they didn't have an epiphany about its uses, and this had to happen a ton of times before anyone thought to use it. Anyway, if you can make fires reasonably easily, you can probably also use them to keep at least some predators at bay, which is handy if you have predators who eat you. It's awful though if you are a big apex predator with great nocturnal senses. Predators tend to fall into two camps: ambush predators and pursuit predators. A spider is an ambush predator. It waits till something falls into its web. Cougars are usually ambush predators too. Humans are pursuit predators. We chase our prey, and we are a subtype of it called a persistence hunter. Your cat is a pursuit predator too. It will stalk something, then leap out and chase it if it tries to flee, but not for long. Humans keep chasing. We literally used to chase our prey till it got exhausted, and then go kill it. That is how we could take out giant woolly mammoths. Something bigger than an elephant, which also travels in packs, is not terribly afraid of sharp sticks. We are also the only primate that does persistence hunting. We are very good at it. Humans are excellent at jogging for hours, and we can get rid of heat fast, part of why we can both support a giant brain, which gives off a ton of heat, and benefit from fire to stay warm. We would go startle a pack of animals and give chase. They'd usually outrun us. We'd catch up and scare them into running again. We can do this all day. We can make frightening noises, communicate over large distance by speech, set fire to things to scare our prey more, and just keep jogging after them till one breaks a leg or literally runs itself to death. And yes, lots of animals can do that. They just keep going until they stroke out. Humans don't. We pace ourselves and can literally jog all day if in good shape. Of course, dogs helped a lot too. Fire scares, but dogs warn. They were good at alerting us when some predator was nearby so it didn't come in and eat us. And they are pursuit predators too. They are good at finding small critters, an extra source of food, at tracking critters, at scaring them away in the night, and also handy for both harassing animals we are chasing and transporting the carcasses. Yes, we use dogs as one of our original beasts of burden. It's even hypothesized that since humans use eye contact followed by moving our gaze as one of our most basic silent communication tricks, and dogs are one of the few critters that understand that trick, that it could have helped us a lot with our hunting. Animal domestication is rightly considered one of our big steps to civilization, and that did start with dogs, presumably those brave enough to approach us, or let us approach, but not so aggressive as to attack. Keep in mind, that's fairly peculiar behavior too. A lot of animals don't even like to come near their own species, let alone another they are not planning to eat. Why did humans keep animals around and alive? How many other species who also shared our other characteristics would? Would we have gotten civilization without that? Now, of course, to get civilization, we needed agriculture, which means settling down in one place. Cats were very handy then, since they eat the vermin that were attracted to our food stores and garbage. It's been suggested that a lot of the foods we ate, and to put it bluntly, did not entirely digest, grew in our waste, and we harvested these when we come back to a campsite the next year. It has also been suggested that thousands of years of gathering the things we got more food value out of selectively bred them to be easier to digest. A lot of those early cereal crops weren't very easy to eat nor terribly nutritious. Of course, we also have Firestick Farming. We are a bit of a pyromaniac species and we use that for hunting, but we probably also noticed that when we torched a forest, it tended to come back as savanna grass plains that a lot of grazing animals thrived better in. So some places we did forest gardening, and others we torched the place and grew us grass-eating herbivores. Presumably at some point we figured out that we could cut out the middleman and eat some of those cereal grasses ourselves. Many uncertainties remain, but needless to say, we eventually started hunting less in favor of keeping our meat animals around and growing crops for them and us to eat. This allowed permanent settlements and more people, both of which are handy since the latter allows more specialization and the former means you don't have to limit all of your possessions to that which you can carry. I said earlier it took us a long time to go from fire to ceramics and metalworking, but it is worth remembering that it is kind of hard to drag an anvil or kiln with you every day, and the work you can do without those is fairly limited and inferior. So you get cities and specialists, and eventually writing, so that you can pass knowledge on to people who aren't physically present at the time, and don't have to remember things our brains aren't well designed for, like exact numbers of how many cows Bob brought into town last year, and if he paid his taxes on them. Which is probably what most early writing was interested in, not technology, personal journals, or literature. At this stage we think of technology as fairly inevitable. People clearly can pass technology over great distances in both space and time, and also clearly know its value. Twin to that, most talks of Dark Ages and lost technology are 90% malarkey. The European Dark Age is mostly a romantic myth made up during later periods, and what little truth to it there is still ignores that chunk of the planet is not the entire planet, or even a particularly large chunk of it. It has happened, of course. There was some loss in the Dark Age, and we've got examples like the Indus Valley civilization that clearly got quite advanced then just fell to pieces. Yet by and large, useful technology does not get lost. It gets lost because it isn't useful to people who have it at the moment. Aqueducts did not get casually forgotten. They just aren't that useful in a lot of places and circumstances. Ditto, giant buildings composed of arches are a bit of a niche application. So we do not want to assume civilizations can't lose technology, and that once you have it you become totally invested in improving it. Only maybe the last 10 to 20 billion humans alive, out of maybe 100 billion who ever lived, have been of the technology addiction mindset, and even that is probably being generous. They knew technology was handy for all of human history at least, that being defined as the times and places we kept written records, which did not include most of the planet until relatively recently, even compared to the 4,000 or 5,000 years we've had it at all. Many of them just didn't think on it much. They had what they had and no one was going around inventing new things constantly. But some outright rejected it. After Rome burned down, or one of the times anyway, the one Nero may or may not have caused, an engineer approached Emperor Vespasian with some devices that would make transporting construction materials cheaper. Vespasian, who mind you was generally considered one of the saner emperors, rejected it, saying he needed to feed his commoners. They needed work to eat. Now this is coming from a Roman emperor, guys not generally noted for being concerned about the common people, and also coming from one of the more engineering-oriented civilizations. In that light, we probably shouldn't assume advanced technology was inevitable for humans, or that every civilization with the talent for it will pursue it to modern levels either. Similarly, the Fermi paradox is not actually about detecting modern civilizations, but ones that have gotten advanced further than us. We would have problems detecting ourselves more than maybe 100 light years away, and could miss ourselves even closer. So we have to advance further ourselves, and of course we might abandon that path or destroy ourselves first. If most alien civilizations destroy themselves at our level of development, or shrug and say they have enough technology, or if they actually hit a brick wall on development, then there's no Fermi paradox. We would simply not see those civilizations when we peer through our telescopes at them unless they were right next door. Now, I've discussed before all the doomsday options in one of the first episodes on the channel, Apocalypse How, and we may revisit them in more detail in the future, but we usually bypass any consideration that we should stop progressing technologically if we were alive. None of us believe science is done yet, but there is a bit of an article of faith implied there. If I said we know all we could learn of science in another generation or two, everyone would laugh, and I'd join them. But we want to avoid assuming there is always another mystery and that every answer brings two more questions. Thinking that itself is a terribly unscientific viewpoint. We can hypothesize a time when we have learned everything, or hit a brick wall on further development, and that could be inside the next couple centuries. However, that does not matter to the Fermi paradox unless that knowledge includes learning some things we think are in reach really are not. No fusion power, no self-replicating machines or nanotechnology, no extending people's lives or freezing them and waking them up. Fundamentally, if you've got those, even just some of those, you can do interstellar travel and shoot for Kardashev 2 civilization status, and that does make the Fermi paradox real. If not, if technology does hit a brick wall, there is no paradox. And I can say it, but I don't believe it, so the paradox is real for me. Now the last option there is that just about everyone gives up on advancing technology. That's hard for me to accept too, and I think for most of my audience as well. For me, for us, the notion of turning away from the technological path is something so hideous that I can only regard it as essentially heresy, unthinkable, morally bankrupt, cowardly, even evil. It would be the most absolute rejection of so many of the ideals we hold as underlying everything our modern civilization stands for. And yet when I think of folks worried about automation taking jobs, a concern I myself share, I do think of Emperor Vespasian rejecting a cheaper means of mechanical transport to feed his people instead. The obsolescence of occupations, such as took place during the Industrial Revolution and is happening now with self-driving vehicles and general automation, can also lead to the disenfranchisement of people, which has and probably will lead to pitchfork riots. If people associate technology with a negative, they can intentionally turn from it. There is also that other nagging background concern when we talk about automation too, that we might get automation so good it thinks for itself and is smarter than us, and either eliminates and replaces us, or even if benevolent, just reduces us to overfed, happy, useless pets. We'll talk about artificial intelligence and such concerns more next month, but I could see a lot of civilizations looking at their level of technology, whose fundamental purpose is to make their lives better, safer, and more convenient, and just saying, enough is enough. Anything more sticks us too close to a precipice, someone might push us over. I'd rather be inconvenienced than irrelevant or redundant. I don't see that happening often, and have difficulty imagining it happens every time, and that every civilization abandons technological advancement and does so before getting off their own home planet. But I think that argument probably does happen every time, and pretty much has to happen at about this technological level. We shouldn't rule that out. As it approaches, folks, even those who are otherwise very pro-technology, grow cooler and more hostile to further advancements and decide to stop short of artificial intelligence and any technologies that would make it too easy for someone to make one, or make a tailored virus, or a swarm of grey goo nanorobots or homemade nukes. I cannot see wiping oneself out as a great filter, with the sole exception of some sort of suicide pact technology that looks amazing, is easy to develop once noticed, and invariably kills everyone. I also can't see artificial intelligence as any sort of filter, since it simply replaces a species, same as we replaced Neanderthal. But while I don't find it likely, I could see intentionally shutting down further tech advancement as a possible last great filter. Again, I don't think so though. No, for my part, to summarize both this episode and the two before it, I tend to think we have an awful lot of hurdles and filters to getting where we are now, and that almost nobody ever has, and probably no one in this galaxy or its nearest neighbors, maybe even the whole supercluster. I think the filters are done, and probably have been since we first started settling down in those first towns that became cities. I don't think it was any one thing, but I tend to suspect the two big ones are the conditions for a planet to be plausibly able to support civilizations arising, and that final jump from smart ape to proto-human, and having it happen to a species that was improbably biologically configured to benefit most from basic technology where many others would not. Those are the only two genuinely unique things we have, unless abiogenesis really does turn out to be a super improbable fluke. A planet with the right size and conditions and location in time and space to nurture massive biodiversity over very long times, and critters capable of genuine abstract thought in bodies and social structure very suited to benefit from it. We simply do not know enough to say, and perhaps that's part of the appeal to the Great Filter and Rare Earth approach for me. It is the camp I subscribe to, but while there are a lot of uncertainties and shaky reasoning, it does not seem fatally flawed in any way, whereas pretty much every other solution I've ever heard of tends to seem that way. We cover the rest of those in the Fermi Paradox Compendium, and we'll look at more of them in more detail down the road, and we will try to give them a fair shake. But to me, the Great Filters seem the best candidate, and if it does not to you, then I hope by now you can at least see why it appeals to a lot of us when contemplating this topic. Next week, we will be taking a look at interplanetary civilizations with a follow-up on the space warfare episode, Interplanetary Warfare. For alerts when that and other episodes come out, make sure to subscribe to the channel. If you enjoyed this episode, hit the like button, share it with others, and try out some of the other Fermi Paradox or Alien Civilization series episodes. And don't forget to check out Peter Watt's Blindsight, our Audible Book of the Month. Until next time, thanks for watching, and have a great week.